Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 4, section 6, which is a summary of curve sketching. All right, so in the last couple of sections, we've been discussing how to find different aspects of our functions, right? We discussed where it's increasing, where it's decreasing, where it might have different kinds of concavities. So what we want to do is we want to put all of those things together and and be able to actually sketch a graph on our own, right? So first, let's discuss what some of these functions might look like. What some of these curves. If I have that f prime of x is greater than 0 and f double prime of x is also greater than 0, well, what does this mean? This is telling me that it's increasing and it's concave upwards. So if I have something like that in a region, well, the function is going to look something like this. Increasing, right? So we have positive tangent slopes and concave upwards. So curve this way, right? If we have f prime of x being greater than 0, but f double prime of x is less than 0, what does that tell us? Well, increase concave downwards. So what would that look like? Well, increasing concave downwards will look like this, right? It's still going upwards from left to right. The tangent slopes are still positive, but now it's curved the other way. What else? Let's say that we have f prime of x is less than 0, but f double prime of x is greater than 0. So what is this telling us? It is decreasing concave upwards. Decreasing concave upwards looks like this, right? Decreasing concave upwards. Tangent slopes are negative, and it has a positive concavity. And finally, if I look at f prime of x being less than 0 and f double prime of x being less than 0, what does that tell me? That tells me that we're decreasing concave downwards. Decreasing concave downwards looks like that, right? So these are essentially the four scenarios of what a function might look like at any given moment, right? A curve in general. So when we're curve sketching, so these are all things that we need to keep in mind. What else do we want to keep in mind? Well, what we want to keep in mind is the domain. All right. So along with the domain are there any discontinuities, right? We want to figure out the x-intercepts, the y-intercepts, um, any asymptotes, so horizontal, vertical, slant asymptotes. All right. What are the critical points? What are the inflection points? Right. And along with the critical points where it's increasing or decreasing, right? And with the inflection points along with that, whether it's concave upwards or concave downwards. Also, along the vertical asymptote, are there going to be, is it going to be going up to infinity or down to negative infinity? Along with the horizontal asymptote, is it actually an asymptote or is it just a discontinuity? So in here, I guess I should also be talking about any removable discontinuities. All right, so these are all different aspects that we need to keep in mind when we're sketching something. So let's go ahead and sketch something. All right, um, here we go. Let's say that I had this A. I've got f of x is equal to, we'll start easy, x to the fifth minus 5x. All right, x to the fifth minus 5x. So what do we want to do here? Well, let's go through this list, right? But we want to keep this in our head. So let's see, what do we want to do? The domain. The domain here is, well, we have a polynomial. With polynomials, the domain is all real numbers, right? What else did we want? We wanted intercepts, right? So let's figure out some intercepts. The x-intercept is when y is equal to 0. Okay, so let's set this equal to 0. X to the fifth minus 5x equals 0. Factor in x. Solve for x. So I get either x equals 0 or x to the fourth minus 5 is equal to 0. From here, that tells me that x to the fourth is equal to 5, which really tells me that x is equal to plus or minus the fourth root of 5. Remember, when we're taking even roots of an equation, we have to include the plus or minus. All right. And what does this give us? Well, it tells us some points here. If I plug in 0, I'm supposed to get 0 for the y, right? Because that's how I found it. If I plug in positive fourth root of 5, I end up with that, and the negative fourth root of 5, I also end up with 0, right? These are all our x-intercepts. What else? Y-intercepts. Well, the y-intercept is when x is equal to 0. So plug that in and see. Well, what we need there is just f of 0. Plug it in, we get 0, which we already knew. 0, 0. All right, so that's the intercepts. What else do we need to check? Asymptotes. So horizontal asymptote. Well, for the horizontal asymptote, that means we gotta take the limit as things go to infinity. But in this case, we're working with a polynomial. Polynomials have no horizontal asymptote, so not applicable. Vertical asymptotes, also not applicable because the vertical asymptotes would happen wherever we have discontinuities, right? So there's no vertical asymptotes here. And slant asymptotes, also not applicable. Recall the slant asymptotes happen when we have rational functions, right? And the degree on top is bigger than the degree on bottom by exactly 1, which we don't have in this case because this is not a rational function. It's a polynomial. So, all right. So those are some of the basic things that we wanted. Now, what else? What else do we need here? We need to figure out critical points, all right? Because we want to figure out where it's increasing or decreasing. So critical points, that's where f prime of x is equal to 0 or undefined. All right, so let's figure out what f prime of x is. And if you recall, what was the function? X to the fifth minus 5x. So the derivative would be 5x to the fourth minus 5, right? And then here, well, let's set that equal to 0. And what does that give me? Well, if I divide everything by 5, I end up with x to the fourth minus 1 is equal to 0, right? And to solve this, well, I can factor this to x squared plus 1 times x squared minus 1 equals 0. This first part gives me no solution, no real solution. And the second part gives me that x is equal to plus or minus 1, right? That's x plus 1 times x minus 1. So there we go. X is equal to plus or minus 1. Now in here, what does that give us? Well, let's see. When x equals 1, so I plug in 1, f of 1. Recall that our function was, what was our function? X to the fifth minus 5x? Yes. So 1 to the fifth minus 5 times 1. So that's 1 minus 5. It's negative 4. F of negative 1. Plugging that in here. So I end up with negative 1 to the fifth minus 5 times negative 1. Negative 1 to the fifth, I have a negative raised to an odd power, so it stays negative. 1 to the fifth is 1. So I have negative 1. And then negative 5 times negative 1 is positive 5. Negative 1 plus 5 is 4. So now we've got our actual critical points. We've got the points 1, negative 4, and 1, negative 1, 4. All right, so that's critical points. The next thing, inflection point. Actually, hold on. Before we move on to inflection points, let's figure out the increasing, decreasing for this. All right, like where things are increasing or decreasing. So I'm going to plug things into f prime of x, and I want to test around my critical values. And my critical values were negative 1 and 1. So to the left of negative 1, I can check negative 2. In between those two, I can check 0. Above 1, I can check 2. And we're plugging them into the derivative, right? Here's the derivative. 5x to the fourth minus 5. If I plug in 0, 5 times 0 is 0. 0 minus 5 is negative, so negative. So that's decreasing there. If I plug in negative 2, negative 2 to the fourth is 16. 16 times 5 is a big number. And when I subtract 5 from that, well, 16 times 5 is bigger than just 5, so that's going to be positive. And then when I plug in 2, 2 to the fourth is 16. I end up with the same exact scenario of 5 times 16 minus 5. So I end up with here positive again, which tells us it's increasing. So notice that in there we've got our intervals of increasing, right? It's increasing from negative infinity to negative 1, and then again from 1 to infinity. It is decreasing between negative 1 and 1. All right, so now let's do inflection points. The inflection points are where f double prime of x is equal to 0, right? And let's figure out what f double prime of x is. Well, what was f prime? F prime was 5x to the fourth minus 5. So the derivative of that is going to be 20x to the third. And that's it, 20x to the third. And if I set that equal to 0, I end up with x equals 0, which gives me the point 0, 0. I already knew that because I calculated that before, right? When I plug in 0 into the function, right? I plugged it in here. Well, I found it there, and I also checked it over here. All right, so that's the inflection point, 0, 0. Now let's figure out the concavity based on that inflection point. So I'm going to plug this into the second derivative, and perhaps I'll shift this down a little bit. All right. And in here, let's see, I'm going to test around 0, right? Because that was our inflection point. To the left of 0, I can plug in negative 1. To the right of 0, I can plug in 1. And if I plug in negative 1 cubed, that's negative 1. 20 times negative 1, that's negative. Plug in 1 cubed is 1 times 20, that's positive, right? So now we've got a lot of information here. We've got that the concavity changes here. We've got about the information about increasing, decreasing. I should also mention here, in here, this is going to be a relative max, right? Because it went from increasing to decreasing. And this is going to be a relative min, because it went from decreasing to increasing. Okay, so let's see what we can do now. Let's sketch this. And let's see. I should also say negative concavity means it's facing downward and upwards. Okay, fine, good enough. Let's get our graph. What do we know about this graph? Let's see. We knew some intercepts, right? We had 3x intercepts as 0, 0, radical, 4th root of 5, and negative 4th root of 5. So 0, 0, 4th root of 5, and negative 4th root of 5. So this is going to be 4th root of 5, and this is negative 4th root of 5. And let's rewrite that. Negative 4th root of 5. Okay, fine. So those are our intercepts. What else do we know? We know y-intercept. Already got that. Asymptotes, none. Critical points. Well, we have them at 1, negative 4, and negative 1, 4. Okay, so let's say that 1 is around here, and negative 1 is around here. And by the way, how do I know that? Well, the 4th root of 5, that's going to be bigger than the 4th root of 1. And the 4th root of 1 is 1, so that means that the 4th root of 5 must be to the right of it. All right? And at 1, we have a value of negative 4. And at negative 1, we had a value of 4. Right? And these are not drawn to scale. Then what else do we have? Well, in here, increasing, decreasing stuff, we're going to be looking at both of them. We're increasing up until negative 1 with a negative concavity. Up until negative 1, we're increasing with a negative concavity. So something like this. Maybe I'll exaggerate this a little bit and move this point over. Nope. So first let me erase this. And I will shift that over. And we'll make it all the way over here. All right. So that's going to be that point. All right. So in here, we said increasing negative concavity. So increasing with a negative concavity. All right. And then after that, what do we have after that? Let's see. Move. There we go. Sorry, I'm fighting with technology over here. All right. Then after -1, from -1 all the way up to 1, we are decreasing. But from -1 all the way up until 0, it's still concave downwards. Okay. So in here, we're decreasing concave downwards. So essentially something like that. Decreasing concave downwards. And then what? Up until 1, we're still decreasing. But now that we're above 1, now that we're above 0, we have a positive concavity. So we're still decreasing, but with a positive concavity. So what does that look like? That looks like this. Decreasing, positive concavity. All right. And then after that, let's shift this again, just like I did before on the other side. Okay. And then after that, what do we have? We still have a positive concavity because we're still above 0, but after 1, we have increasing. So increasing with a positive concavity, well, that's going to look like this. All right, that's increasing with a positive concavity. And there you go. That is the equation of our graph. All right, this is f of x is equal to x to the fifth minus 5x. And what we want to do here is we want to label things. Here is our local max. Here is our local min, or relative max and relative min. These are our intercepts, right? So we have these 3 x-intercepts, but more importantly, this intercept right here is the inflection point. All right. All right. So that's that one. Next one. Let's see. Example B. So that was A. So example B. Let's say that we have this. F of x is equal to x squared minus 6x plus 12 over x minus 4. All right, so right away, I want to say, well, what's the domain? The domain is x cannot be equal to 4, right? Because that would make the denominator 0, and we don't like that. Next thing, let's see. Let's find some intercepts. So the x-intercept is when y is equal to 0. So let's set this function equal to 0. X squared minus 6x plus 12 over x minus 4. Set it equal to 0. Now look at that. What do we have? We have a fraction equaling 0. The only way for a fraction to equal 0 is if the numerator itself is equal to 0. And now let's see, can we factor this to solve this? Well, two numbers that multiply to 12 but add up to -6. Ooh, that's a toughie. That does not happen. There's no two numbers that multiply to positive 12 but add up to -6. So what we need to do here is use the quadratic formula. And what does that give us? Well, we're going to say x is equal to the negative of b plus or minus the square root of b squared minus 4 times a times c. All of this over 2 times a. Right? And what does that give us? Well, let's see. Negative 6 is positive 6. Plus or minus the square root of -6 squared, that's 36, minus 4 times 12 is 48. All of this over 2. Notice here that 36 minus 48. 36 minus 48 is -12. And I've got a square root of -12. That doesn't work. So this is not a real number. which essentially implies that there's no x-intercept, right? Because there's nothing that made our function 0. There's no real number that made our function 0. There is a complex number that would make this 0, but again, in calculus overall, we don't consider complex numbers. Now, let's figure out the y-intercept. The y-intercept is when x equals 0. So that's easy. Plug in 0 for x. What does that give us? Well, 0 minus 0 plus 12 is just 12. And then 0 minus 4 is negative 4, which reduces to negative 3, giving me the point of 0, negative 3. All right, cool. So that's our intercepts in our domain. Let's figure out if this has any asymptotes. So let's start with the horizontal asymptote. And the horizontal asymptote, recall that it's when the limit as x goes to infinity of f of x. Or, well, I should say as x goes to either plus or minus infinity. That would save us some writing. Plus or minus infinity. Alright, so let's see. If I take the limit as x goes to infinity of x squared minus 6x plus 12 over x minus 4. Well, what I need to do here is multiply by 1 over x over 1 over x, right? And the reason for that is because I can't just plug in infinity. I end up with infinity over infinity. That doesn't help us. That doesn't tell us anything. So if I multiply everything by 1 over x over 1 over x, what does this give me? Well, this gives me the limit as x goes to infinity of x minus 6 plus 12 over x over 1 minus 4 over x. And now, as x goes to infinity, well, this piece goes to 0, this piece goes to 0. However, this piece does not. If I let x go into infinity here, I still have that x minus 6 there. So this actually goes to infinity. So, it does not exist. A very similar thing happens here whether or not we were going to positive or negative infinity, right? In both scenarios here, those little fractions end up going away, right? If I was going to, so when I went to positive infinity, I had infinity minus 6 plus 0, right? But it was positive infinity. But if I go to negative infinity, so if I say take the limit as x goes to negative infinity of this stuff, I'm going to skip to this step. X minus 6 plus 12 over x over 1 minus 4 over x. Well, the same stuff happens with these little fractions. That goes to 0, that goes to 0. But now, as we're going to negative infinity, well, negative infinity minus 6 is negative infinity, which again does not exist. It's not a real value. So what that tells us is that we have no horizontal asymptotes. Okay, what about vertical asymptotes? So let's see, vertical asymptotes. And vertical asymptotes, remember that they were the limit as x approaches our discontinuities from either side, from the right or from the left of our functions. All right, so let's see what that means for this scenario. What was our discontinuity? Well, based off of the domain, the discontinuity happens at 4. So we're going to take the limit as x goes to 4 from the right of our function, which was x squared minus 6x plus 12 over x minus 4. And we're also going to do it from the left of x squared minus 6x plus 12 over x minus 4. All right. So in here, let's see. We already know that, where is it? That there's no x-intercepts, right? How is that helpful? Well, this part over here, that x squared minus 6x plus 12, that's by itself, it's a parabola, right? So either it's always positive or it's always negative because that parabola by itself, right? That's what I found over here. This parabola by itself it never touches the x-axis, so it's either always above the axis or always below. Because we have this being a positive value here, I know that it's always above the x-axis because it needs to be facing upwards. And again, I'm just talking about this parabola right here, not the function over x minus 4. Because in here, what I'm getting at is that this value of x squared minus 6x plus 12 is always going to be positive, irrelevant of anything else. So this is always positive. The numerator is always positive here. All right, but now let's approach 4 from the right. 4 from the right is something like 4.1. 4.1 minus 4, that's positive. Overall, this is going to go to positive infinity. On the bottom, 4 from the left, something like 3.9. 3.9 minus 4, that's negative. So overall, this goes to negative infinity. All right. Now, how do I know that there were vertical asymptotes? How do I know that this wasn't a removable discontinuity? Well, if this had been a removable discontinuity at 4, then we would have had this x minus 4 somehow cancel with the numerator. We would have been able to factor the numerator into x minus 4 times something else. But the numerator, as we already discussed earlier, is not factorable. So because it's not factorable, this x minus 4 would not get canceled out. So therefore, there are no removable discontinuities. So the discontinuities that we have must be asymptotes. And that's how I know that these have to go to some sort of infinity. All right, so that's our vertical asymptote. Slant asymptotes. Let's see. Does it apply here? Well, if you recall, slant asymptotes were where when the numerator was bigger than when the degree of the numerator was bigger than the degree of the denominator by exactly 1. And that is exactly what's happening here, right? The degree of the numerator is 2, the degree of the denominator is 1, so it is bigger by exactly 1. So what we want to do here is we want to do long division. So x minus 4 into x squared minus 6x plus 12. And as we do this long division, well, what do we do? We say x into x squared, x. X times x is x squared. X times negative 4 is negative 4x. Subtract negative 6x plus 4x, right? Minus negative is plus. I end up with negative 2x plus 12. X into negative 2x is just negative 2. Negative 2 times x is negative 2x. Negative 2 times negative 4 is positive 8. Subtract. Negative 2x minus negative 2x goes away. 12 minus 8 is 4. So in here, what we end up with is that our function is really the same thing as saying x minus 2 times, x minus 2 plus 4 over x minus 4. All right, and if you recall, the way to find the slant asymptote here is, well, technically as x is going to infinity, this right here goes to 0. So this right here is my slant asymptote. Y equals x minus 2, right? Cool. So now we've done the asymptotes. What's next? After the asymptotes, we got to find some critical points. So we got to find our critical points. So critical points. Critical points are where f prime of x are equal to 0 or undefined. So let's see. What is f prime of x? Well, we need to do the quotient rule, right? Because we've got a quotient. So the derivative of the top, the derivative of x squared minus 6x plus 12 is 2x minus 6 times the bottom, and the bottom was x minus 4, minus the derivative of the bottom, the derivative of x minus 4 is just 1, times the top, which again was x squared minus 6x plus 12. There you go. All over the bottom, squared. All right, so now that we have this, let's see what we can do with this. We can expand the numerator, right? We can expand the numerator by multiplying everything out as much as possible. So in here, 2x times x, 2x squared, 2x times negative 4, negative 8x, negative 6x times x, negative 6x, negative 6 times negative 4 is positive 24. Cool. Distribute this negative 1. negative x squared plus 6x minus 12. All of this over the bottom squared. Never expand the denominator, always expand the numerator. Alright, so you want to expand the numerator there so that we can see if we can factor anything out. Alright, so let's reduce. Let's see, what can we combine in the numerator? On the bottom, easy, it's just x minus 4 squared. On the numerator, 2x squared minus x squared, that's just x squared. Negative 6x plus 6x. Those cancel each other out, and we're left with just negative 8x. The constants, 24 minus 12. 24 minus 12 is positive 12, right? And now, let's see. In here, I can actually rewrite this. This actually becomes x minus 6 times x minus 2. All of this over x minus 4 squared. And why do I care about that? I care about that because, well, I want to set this equal to 0, right? So let's see what happens when we set that equal to 0. If I set that equal to 0, I get, well, a fraction equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0, which tells me here that either x equals 6 or x equals 2, right? All right, so now to figure out where these points are, because these are just critical values, we need to plug them into the original function of, where is it? Of x squared minus 6x plus 12 over x minus 4. You should verify that this is what you get. All right, I'm going to leave the calculation out here. So when we plug in 6, you are going to get a 6 as your final answer. And when I plug in 2 into the function, you're going to get negative 2. And again, in here, we're plugging into f of x. So to go from here to here, plug into f of x. All right, so now, what's the next thing that we need to look at? Well, what we found there was where f prime of x is equal to 0. The next thing is there anywhere where it's undefined? Well, yeah, at 4 it's undefined, right? Because I can't plug in 4 here. But 4 is not part of my domain, so I don't need to worry about that. But I do need to test around it. So I don't need to worry about it in the sense that that's not a critical value, but we do need to test around it. So we get test around 2, 4, and 6. And what we can test here, well, the easy values, 0, 3, 5, 7. All right, cool. And we're testing all of these into f prime. Now let's look at the f prime, right? This was the factored version of f prime. In here, the denominator is always going to be squared. Irrelevant of what happens on the inside, it's going to be squared, telling us that the denominator is always positive. Which means that all we need to do is look at the numerator to see what's going on. So let's plug in 0. 0 minus 6 is negative 6. 0 minus 2 is negative 2. Negative 6 times negative 2 is positive. So it's increasing there. Let's plug in 3. 3 minus 6, negative. 3 minus 2, positive. Negative times a positive, negative. So decreasing. Plug in 5. 5 minus 6, negative. 5 minus 2, positive. Negative times a positive, negative. 7. 7 minus 6, positive. 7 minus 2, positive. Positive times positive, positive. So it's increasing. All right. So there we go. Now we know where things are increasing or decreasing, right? The intervals here being from negative infinity to 2 and 6 to positive infinity as far as increasing goes, and then decreasing from 2 to 4 and then again from 4 to 6. Notice I split it up when I said it. I didn't say from 2 to 6, I said from 2 to 4 and then again from 4 to 6. Because at 4, we've got a vertical asymptote, so there's nothing happening at 4. All right, so that's f prime. And that was increasing or decreasing. Let's do f double prime. So f double prime, and well, why do we want to do that? Well, because that's going to give us inflection points, right? So f double prime of x. and that's when f double prime of x is equal to 0. Alright, so I'm going to use the quotient rule, but I'm going to use it off of this, x squared minus 8x plus 12. So in here, f double prime of x is going to be, well, the derivative of the numerator. We just said it was x squared minus 8x minus 12. The derivative is 2x minus 8. So that's the derivative of the top times the bottom. The bottom was x minus 4 squared minus the derivative of the bottom, 2 times x minus 4 times 1, and then that times the top, which was x squared minus 8x plus 12. All right, again, I'm just basing all of this off of this formula right here, or excuse me, this expression. And then all of that over the bottom squared, and the bottom was x minus 4. It was already squared, so I got to square it again. Cool. Now, let's see, what can we factor out here? Notice here that this 2 times x minus 8 is really 2 times x minus 4. So I'm going to ignore that. Alright, what can I factor out? I see that I have an x minus 4 and an x minus 4. I also see a 2 and another 2. So really we're going to factor out a 2x minus 4. So what do we get here? We're going to say, well, this is going to give us 2 times x minus 4, right? That's the stuff they had in common, times. Here we have an x squared minus 2. Excuse me, I said that completely wrong. I don't even know why I said that. We have an x minus 4 squared. There we go. And x minus 4 squared, what is that? That is x squared minus 8x plus 16. Minus. We took out the 2, we took out the x minus 4. This one's not doing anything. So I really had to distribute this negative, to all of these. So minus x squared plus 8x minus 12. All of this over x minus 4 to the 4th. Now, at that point, the x minus 4 reduces. That becomes to the 3rd, right? And inside that inside that numerator there, in the parentheses, we've got x squared minus x squared goes away. Negative 8x plus 8x goes away. And we're still left with a 16 minus 12. 16 minus 12 is 4. But then times this 2 out here, we get 8. So we have 8 over x minus 4 cubed. Alright? And again, that's because this 16 minus 12, that's 4 times 2, 8. Alright, so let's set this equal to 0. So when we set this equal to 0, well, we've got a fraction equaling 0, which tells us that the numerator must be equal to 0. But that doesn't make sense. 8 cannot equal 0. 8 is not 0. Alright? So what does that tell us? Well, that tells us that there's no inflection point. But that doesn't mean that we can't test for concavity, right? Because we already know that we should be testing around our vertical asymptotes. So we're going to test around our vertical asymptote here. In other words, around our domain. So we're going to test around 4. And if I plug in, for example, 0 to the left and 5 to the right, what happens to this? Well, plug in 0. 0 minus 4, negative 4. Negative 4 cubed, all that matters is that it's negative. Because now I've got 8 divided by a negative, that's a negative. So in here, that's negative, it means concave down. Plug in 5. 5 minus 4, 1. Cubed, 1. 8 over 1, positive. So that's concave up in that region. So now that we have all that information, now let's see how we can graph this. Alright, and what is it that we know about our function? We knew that there was, so let me scroll up so we can all look at the information. Alright, we knew that at x equals, the domain is x cannot be equal to 4, and we showed that that's a vertical asymptote. What else do we have? We have no x-intercepts. We have one y-intercept, 0, negative 3. So let's go ahead and sketch everything I just said so far. So I said we had a vertical asymptote at 4. So let's say here is 4, and there's my vertical asymptote. What else do we have? We have a y-intercept of 0, -3. So this is at -3. All right, we had no x-intercepts, right? We had no x-intercepts, but what else do we know? We know around a vertical asymptote, well, we have no x-intercepts, we have no horizontal asymptotes, but we do have vertical asymptote. From the right, it's going to positive infinity. From the left, it's going to negative infinity. So from the right, it's going to go up to positive infinity, up this way somewhere. And from the left, it's going to go down to negative infinity. What else do we know? We see that we have a slant asymptote of x minus 2. So let's look at how that looks like on the graph. X minus 2. So x minus 2 crosses at 2. It also crosses at 2 on the x-axis. So it looks something like this. All right. So we got our vertical asymptote. We got our slant asymptote. All right. What happened after the slant asymptote? We've got critical points, and we had them at 6, 6, and 2, -2. Okay. 6, 6, 2, -2. So 6, 6. Yeah. Let's say it's around there. And then 2, -2. So around here. Okay. What else do we have? We have increase. So here we go. So this is the next part. From negative infinity all the way up until 2, we've got increasing. But it's increasing with a negative concavity, right? Because everything before 4 has negative concavity. So from negative infinity to positive 2, it is increasing with a negative concavity. Ooh, let's draw that better. Increasing with a negative concavity. And then from 2 to 4, it's decreasing, right? It's decreasing right there, right from 2 to 4. But not only is it decreasing, it's decreasing with still a negative concavity. So still negative concavity. All right, so decreasing negative concavity. There we go. And this goes down to negative infinity, right? Next piece. From 4 to 6, decreasing above 4, positive concavity. So decreasing positive concavity, well, it'll look like something like this. Right? I guess I'll expand my graph a little bit. So that's decreasing with a positive concavity. And then after that, well, what do we have? We've got increasing and still with a positive concavity. Increasing still with a positive concavity. So we end up with something like that. And remember that we had to approach our slant asymptotes. So we want to make sure that these are getting closer and closer to our slant asymptotes. All right. So that's essentially, now what I wanted to do. That's essentially the graph of our function. All right. What I was trying to get rid of that. Okay, fine. So cool. Next problem. So that was B. C. And I know this. Hold on. I know this seems like it's taking a lot of time to do each of these, but that's because I'm doing them while I'm explaining stuff. Without the explanations, these are actually a lot faster. So f of x is equal to x squared plus 1. X squared plus 1 over x squared minus 4. All right. Sorry. X squared minus 4. Nah, you know what? I'll just leave it as x squared minus 4. I was gonna complicate it, but no reason for it. All right. So let's see. Let's figure out our domain here. Our domain is that x cannot be equal to plus or minus 2, right? Because that's what makes the denominator 0. Cool. Let's figure out x-intercepts. The x-intercept is when y is equal to 0. So I set this entire thing, x squared plus 1 over x squared minus 4 equals 0. And at that point we say, well, we've got a fraction equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0. So x squared plus 1 equals 0. No solution. There's no solution because, well, I guess I can do the very next step that we would have gotten there, which is that x squared is equal to negative 1. We know that's not possible. No solution. That's not possible because any real value squared is at least 0, right? So that's the x-intercept. The y-intercept. The y-intercept is when x is equal to 0. So we're looking for f of 0. Easy. Negative 1/4. Done. So that is our y-intercept. What else do we need? We need to figure out stuff about the asymptotes. So let's figure things about the asymptotes. So let's see. Horizontal asymptote. The horizontal asymptote is when we take the limit as x goes to plus or minus infinity of our function, right? So let's see what we have here. Limit as x goes to infinity of x squared plus 1 over x squared minus 4. Technically here I need to multiply by 1 over x squared over 1 over x squared, giving me the limit as x goes to infinity of 1 plus 1 over x squared over 1 minus 4 over x squared. And as x goes to infinity, this goes to 0, that goes to 0, gives me 1. Notice that in here, if x were going to negative infinity, the same stuff happens, right? These still get canceled and we still get 1. So our horizontal asymptote, whether we're going towards positive infinity or negative infinity, is just 1. Cool. Vertical asymptotes. Vertical asymptotes, well, let's see. We have to take the limit as x goes to our discontinuities from both sides. And what were our discontinuities? Well, we had 2 of them, positive 2 and negative 2. So let's see what happens there. So we're going to take the limit as x goes to 2 from the right, the limit as x goes to 2 from the left, the limit as x goes to negative 2 from the right, and the limit as x goes to negative 2 from the left. All right, and we're doing this for our function, right? And let's see, what was our function? X squared plus 1 over x squared minus 4. All right, I'm going to write it as x squared plus 1 over x plus 2 times x minus 2. All right? So in here, we're approaching 2 from the right. If we're approaching 2 from the right, that means something slightly bigger than 2, right? And again, in here, what you'll notice is that nothing canceled out. So there's no removal discontinuities, meaning that all of these are going to be asymptotes. All these discontinuities are asymptotes. So the numerator, irrelevant of what I plug in, the numerator is positive. So it's always positive. Okay. The denominator, something to the right of 2, 2.1. 2.1 plus 2, positive. 2.1 minus 2, positive. Overall, positive, so it goes to positive infinity. Next one, 2 from the left. We already know that the numerator is always positive, right? And I should not do such a horrible job of notation. There we go. Better. This way I don't have to copy this entire thing down. It's just f of x. So the numerator, we just said, is always positive. The denominator, 2 from the left, something like 1.9. 1.9 plus 2, positive. 1.9 minus 2, negative. Overall, negative. Negative 2 from the right. Well, that's something like negative 1.9. We already know the numerator is always positive. The denominator, negative 1.9 plus 2, positive. Negative 1.9 minus 2, negative. Overall, negative, so it goes to negative infinity. And lastly there, as we're approaching negative 2 from the left of our function, Well, we already said that the top is always positive. The denominator, negative 2 from the left, something like negative 2.1. Negative 2.1 plus 2, negative. Negative 2.1 minus 2, still negative. Overall, negative times a negative is positive, positive over positive is positive. Alright, so there we go. We've got what the behavior is around each of our asymptotes, each of our vertical asymptotes. Slant asymptotes, not applicable. Why is it not applicable? Because in here we have quadratic over a quadratic, right? So the numerator is so the degree of the numerator is not larger than the degree of the denominator. All right, so let's see what we get here. After that, we want to find critical points. So let's find some critical points. The critical points are where f prime of x is equal to 0 or undefined. All right. So what is f prime of x? Well, what was the function? It was x squared plus 1. I'll write it over here. F of x was x squared plus 1 over x squared minus 4. All right, cool. So the derivative of the top, 2x, times the bottom, x squared minus 4, minus the derivative of the bottom, 2x, times the top, x squared plus 1, all of that over the bottom squared, right? And now, let's see what we can do here. I see that both of these have an 2x, so let's factor out the 2x. And what am I left with? I'm left with x squared minus 4 minus x squared plus 1. So I can distribute this negative into each of those, so minus x squared and then minus 1. All of this over x squared minus 4 squared. At that point, I see that the x squared minus x squared cancels each other out. Negative 4 minus 1 is negative 5. Negative 5 times that 2x on the outside is negative 10x, and we have this over x squared minus 4 squared. So now, I want to see where the critical values are, right? So what I need to do here is set this equal to 0. And if I set that equal to 0, I have a fraction equaling 0. And what we know about fractions equaling 0 is that the numerator itself must be equal to 0. So negative 10x is equal to 0. That tells me that x is equal to 0. This gives me a coordinate, which we already found, right? Because when x equals 0, that's our y-intercept, and our y-intercept was negative 1/4. So there it is. That's the point that it gives me. Now, along with the critical points, we have to test for increasing, decreasing, and we're testing here around 0. And we're testing it into the first derivative. Notice that the denominator is something squared, so irrelevant of what happens inside here, right? Even if x squared minus 4 is negative, overall, since I'm squaring it, this square right here is going to be a positive denominator. So when I plug in something like negative 1, I just need to look at the numerator. Negative 10 times negative 1, that's positive, increasing. If I plug in 1, negative 10 times 1, that's negative, decreasing. Right? So, hold on. I messed this up. And I'm going to tell you how I messed it up in a second. We had vertical asymptotes. We have to test around our domain as well. So we were supposed to test around 2 and negative 2 as well. So that's where I messed up. So let's go ahead and fix that. So let's see. We just said we have to test around negative 2, 2, and also 0. Okay, now, let's see. Here, negative 1 and 1. Well, that's exactly what I did before. And we had gotten positive, negative, so increasing and then decreasing. All right. But now, to the left of negative 2, something like negative 3. Well, negative 10 times negative 3 is positive. On the bottom, again, we already said that it's always positive on the denominator. So increasing. To the right of 2, so something like positive 3. Negative 10 times 3 is negative 30, so we have negative, right? The bottom's always positive. So decreasing. All right, so, I mean, it didn't change that much as far as what our what the function was doing, it was still increasing from everything to the left of 2, excuse me, everything to the left of 0. But the difference is that now we're actually showing that at -2, nothing's happening, because at -2, it is not defined. All right, cool. So that is critical points. Let's look at inflection points. And inflection points where the second derivative was equal to 0, right? So let's see, what can we do? Let's figure out the second derivative. And what was the first derivative? It's right here. So maybe I'll write that down here. F prime of x was equal to -10x over x squared minus 4 squared. All right, so inflection points. Second derivative. The derivative of the top, -10, times the bottom, x squared minus 4 squared, minus the derivative of the bottom, 2 times x squared minus 4 times 2x, times the top, -10x, all of this over the bottom squared, x squared minus 4 squared, squared. Cool. Now, let's see, what can we factor out here? We've got a few things that we can factor out. Let's see. I see a -10 and a -10. I see an x squared minus 4 and an x squared minus 4. So what I'm saying is -10 x squared minus 4, -10 x squared minus 4. So we're going to have here -10 times x squared minus 4. And then what are we left with? We're left with, well, I took out this -10. I took out one of these x squared minus 4s. So I still have an x squared minus 4. Minus, on this side, the 2 is still there, the 2x is still there, the x is still there. So 2 times 2 is 4, x times x is x squared, so I have a 4x squared there. And on the bottom, it's just simply x squared minus 4 to the 4th. At that point, we see, well, this x squared minus 4 makes this become to the 3rd power, and then I have x squared minus 4x squared. So I have -10 times x squared minus 4x squared is -3x squared, and then we still have that minus 4 over x squared minus 4 to the 3rd. In the numerator, distribute that -10. What does that give me? That gives me positive 30x squared plus 40 over x squared minus 4 cubed. If I try to set this equal to 0, well, that would tell me that the numerator has to equal 0, right? 30x squared plus 40. But that would mean that x squared is equal to -4/3, right? Move the 40 over, divide by 30, -4/3. But this has no solution, which tells us no inflection points, all right? And now what can we say about that? Well, so there's no inflection points, but that doesn't mean that we can't figure out anything about concavity, because recall that for concavity, not only do we test around the inflection points, but we test around the domain. And we know that we have asymptotes at -2 and at 2. So we could test around that. In here, in this fraction, notice that the numerator is always positive, right? Because I'm taking some value, squaring it, that's positive, times 30, positive, plus 40, positive. So in here, numerator is always positive, all right? Even if x is 0, the numerator is always positive. So what can we test? We can test 0, we can test 3, we can test -3. And when I plug in 0, well, I just said the numerator is always positive, so all we got to check is the denominator. 0 minus 4, -4. -4 cubed, well, a negative to an odd power is still negative. So negative, which means concave down. Plug in -3. -3 squared is 9. 9 minus 4 is 5. 5 cubed is still positive, right? And we knew the top was already positive, so here it's always positive. Plug in 3. 3 squared is 9 minus 4, 5. Same exact scenario that I had on this piece, so it's still positive on that side. And now we've got what our concavity looks like. All right, cool. So let's sketch this. And in here, what did we have? Well, we already knew that we had two asymptotes, one at -2 and the other one at 2. And what else did we know? We knew some things. Let's see, let's start from the very top. Oh, not there. No x-intercepts, okay. A y-intercept at 0 or -1/4. We'll keep that in mind. A horizontal asymptote of 1. Ooh, that's already a lot of information. So we had at 0, -1/4, we've got a coordinate. Let's say that that's 0, that's at the height of -1/4. And we also said that we had a horizontal asymptote of 1. So let's get that horizontal asymptote in there. All right, and this is at 1. Cool. So now what? So y-intercept, horizontal asymptote. All right. No slant asymptote, but we do have some behavior. To the right of 2, we've got positive infinity. Okay. To the right of 2, we've got positive infinity. To the left of 2, we've got negative infinity. Negative infinity. To the right of -2, where is it? There it is. To the right of -2, we've got negative infinity again, and on the other side, positive infinity. All right, so to the right of -2, negative infinity, and from the left, positive infinity. All right. Next thing, what do we know? We need to figure out some concavity issues, right? And some increasing, decreasing. So we're increasing all the way up until 2, and then again from 2 to 0. Okay, but let's figure out just this first part. We're increasing all the way up until 2, and we've concave up all the way up until 2. Increasing concave upwards, and we must have this horizontal asymptote. There we go. Increasing concave upwards with that horizontal asymptote. From -2 to 0, we're still increasing, but now we're concave downwards. Still increasing concave downwards, and we know that we have to reach this negative infinity. So there we go. From 0 to, well, I passed it. There it is. From 0 to 2, we have decreasing with a negative concavity, right? 0 to 2 is still here. So decreasing with negative concavity. Decreasing with negative concavity. And it has to approach that value, right? Negative infinity there at 2. And then after that, we still have decreasing, but now we've got it with a positive concavity. All right. So there you go. That's the graph of this function. That, I mean, that's the examples that I will do for this. But I want to just recap here. This is something that you really want to keep in mind. All right. Because as you saw, like when I went to actually sketch things, I was really looking at whether it was increasing and what kind of concavity it had to draw what kind of curve I was working with. All right. So you really want to keep these things in mind. All the other stuff is just finding points, finding derivatives, and things like that. That's, I mean, it's super important too. But when it comes to actually sketching and already having all the information, you want to always keep in mind what that curve would look like in that region. All right. All right. So this will be, I guess I want to scroll the way down first. This is the end of this section. All right. That's 4.6. There are obviously a lot more other kinds of scenarios, all right, in here. So I do encourage you to look at other kinds of examples. All right. But that's the end of this section. All right.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, But more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.